Welcome to another Tech Ambrosia Quick Sip. Today I want to talk really briefly about PWM, Pulse Width Modulation. Have you ever wondered why your LED lights flicker on camera, but not in real life? Or why electric cars and hybrids make such strange noises at low speeds? Or what these two things have to do with Lady Gaga? Probably not, but it's PWM all the way down, baby, and we're going to talk about it now. All set? Bottoms up. Okay, first a quick overview. What is PWM? Pulse width modulation is a method for electronic control of energy supplied to electrical loads. That's a really generic description of it, and not a terribly insightful one, so let me paint a picture for you. Let's say you have a power source of some kind. Take this battery, for example. This supplies constant voltage along with a maximum amount of current within that voltage envelope. If we connect a load to this power source, say a light or a motor, that load is going to operate at a constant level of output, either the load's maximum designed output, i.e. it'll draw as much current as it needs, or an output level that represents the maximum amount of power the battery or other power source can supply. So if we scale up our battery to, say, household voltage or industrial voltage levels, you can see that controlling the amount of power that gets to the light or the motor or whatever is extremely important. You don't want to plug in your kitchen mixer and have it immediately start spinning at maximum speed. In the past, one method for realizing this control was through the use of a rheostat, a type of variable resistor. These draw in a maximum amount of power from the power source, shed a selectable amount of that power as heat through the variable resistive element, and then output the remainder of that power to whatever your load is. They're very simple, very effective, and very inefficient, especially at high current levels. The astute among you may have observed that your mixer does not, in fact, turn on when you plug it in. There's an on-off switch, either in the mixer itself or embedded in the power outlet, and you're absolutely right. Well, what would happen if we turned that switch on and off rapidly? That brings us to a useful rephrasing of our original definition of pulse width modulation. PWM is when you control the current going to something by rapidly turning it on and off, pulsing it. But an important part of PWM is that it's variable in a specific way. You can modulate the width of the pulses. Pulse width modulation. By switching the power source on and off several 100,000 or even million times per second, it becomes trivial to precisely control how fast, how bright, how loud, or how warm electricity can make something. PWM first entered the market in the early 60s, but it wasn't until the prices of high-speed semiconductors began to fall in the 80s that it really started to take off. These days, PWM is everywhere. Lights, motors, amplifiers, and synthesizers all make use of it in some form or another. You probably haven't even noticed most of them, and that's the point. PWM, when done well, is basically invisible. Partially, this can be credited to PWM circuitry that operates at a frequency that's outside of human ranges of perception. However, most of the time, PWM is imperceptible because it's hidden from you. PWM circuits use a low-pass filter to help smooth out the voltage variations between power pulses. This is entirely the reason your cheap LEDs flicker but your expensive ones don't. A low-pass filter isn't anything exotic, it's just a capacitor and a resistor. The values chosen for the resistor-capacitor pair determine what switching frequency it's tuned for, and how much it smooths out the voltage ripple. That switching frequency itself is completely arbitrary. But within a single PWM circuit, it will not change. PWM only varies how long each pulse is, not how many pulses per second there are. This frequency can be as low as a few times per minute in a toaster oven, all the way up to a couple million times per second in something like a 1-bit digital-to-analog converter, or DAC. The precision afforded by modern PWM is the whole reason we have miniature lights that can mix and display any color our eyes can perceive, and why we control brushless motors so precisely that we can make bricks hover in the air via computers. Alright, so what's the Gaga connection? Bad Romance appears on Gaga's third EP, The Fame Monster, released in 2009. Within the verse, behind the lyrics, I want your love, you can hear a fat, sticky synth pad that lewdly slides downwards behind the vocals. This sound has a history, and it's known as the Hoover sound, or the Dominator. It was pioneered in the early 90s Euro-techno scene. The thick, swirly feel of the Hoover sound comes from its heavy reliance on pulse-width modulation, driven by a fast LFO and plenty of chorus effect. Historically, the sound was created using a Roland Alpha Juno synthesizer, which first launched in 1985. Well, there you have it. From KitchenAids to Lady Gaga, this has been a whirlwind tour of pulse-width modulation. Thank you for watching this Tech Ambrosia Quick Sip. Have a good night.